The basic function of switches is to connect devices to the network. Of course, they can do far more, but every other feature they have is to support connecting devices. Primarily, switches work at layer 2. When we think about layer 2, we think about things like MAC addresses, Ethernet frames, and VLANs. A lot of modern switches support some layer 3 functions. That means IP addressing, routing, and that sort of thing. For this section of the series, we're going to focus our attention on layer 2. We commonly use Ethernet protocols in our networks. Each Ethernet frame has a source MAC address and a destination MAC address. Ethernet, and layer 2 in general, is used to deliver frames from one hop to the next. This means that with each hop, the source and destination MAC will be updated. The source will be the device that's sending, and the destination will be the next hop along the path. This process is called frame rewrite. Switches don't count as hops in this sense. That is, they don't update the source and destination MAC addresses of each frame that passes through them. So what are switches for? Connectivity. All devices need to be connected to each other in some way. But we can't literally connect every device to every other device. Imagine how many cables we would need. Instead, the switch uses a process called frame switching. Instead of connecting devices directly to each other, devices connect to switches. As you can see, this is so much simpler. When a frame arrives at a switch, the switch decides which link or interface to send the frame out of. This makes sure that the frame gets to the correct destination. The next question is, how does a switch know which link to send the frame on? It does this by learning the MAC addresses of connected devices and the interfaces they are connected to. These details are stored in the MAC address table. When a frame arrives at a switch port, the switch takes a look at the destination MAC address. Remember that this is in the Ethernet header. It looks for this MAC address in the MAC address table. Here, it finds the port that the MAC address belongs to. It then forwards the frame out of this port. We should ask ourselves, what happens if the MAC address we're looking for is not in the MAC table? This means that the switch hasn't learned about this MAC yet. In this case, it will flood the frame out of all ports. That means a lot of devices will get that frame. Most will ignore it as it's not meant for them. The correct device will send its reply, which the switch will see. The switch can then learn which interface this device is connected to and add the entry to the MAC address table for next time. Do you want to see what a real MAC address table looks like? From the CLI, we can use the command show MAC address table. Here we can see all the MAC addresses that the switch knows about, and the port that should be used to reach them. Entries don't stay in here forever though. Once an entry is learned, a timer starts. If more traffic involving that MAC address is seen, then the timer resets. But if the timer expires, the entry is removed from the table. This is one way the switch keeps the table fresh. For example, we might have a laptop that we disconnect from one port and then connect to another port. If the MAC address table didn't clean up after itself, traffic might get sent out the wrong interface. If you're planning on taking the Ccna exam, we have a few extra resources to get you ready. These include study notes, quizzes, flashcards, transcripts, and the command line summaries. Check the video description to get a link to each of these resources. Usually quiz explanations are for members of the site. However, I've made all the quizzes in this video available to everyone, so you can see if you like them. We've had a quick review on switching in a simple network, but as networks grow and become more complex, we usually need to divide it up into logical parts. We do this by configuring a VLAN. VLANs create one or more logical networks on a physical switch. It's kind of like dividing a switch into a few smaller switches. Some ports can be part of one VLAN, other ports can be in a different VLAN, and they can both be separate from each other. There are a few reasons we might want to do this. The obvious one is to separate some traffic from some other traffic. This could be for security, or perhaps we have multiple customers that we need to keep separated. We might use VLANs to group certain traffic together. For example, we would create a VLAN just for voice traffic, that is phone calls. This makes it easier to give this traffic a higher priority than other traffic. Or we could group devices into VLANs. It's quite common to put servers in one VLAN, printers in another, and PCs in yet another VLAN. This is often done so we can put a firewall between these VLANs and apply security policies between them. We'll take a look at security policies more in a later section of this series. Think about broadcast domains. As we know, broadcasts are limited to the local network. Each VLAN is considered to be a different network, so creating VLANs creates smaller broadcast domains. There are many different reasons we might want to use VLANs. Don't worry too much about listing them all out. As you gain experience, you'll start to appreciate their value and when to use them. For now, we're just going to focus on how they work and how they're configured. In the switches CLI, we're going to create 3 VLANs with IDs 10, 20, and 30. This is as simple as typing VLAN and the VLAN ID. We can optionally give each one a name. I recommend this as it makes it easier to see what each VLAN is for later on. If you're not yet familiar with Cisco's command line interface, I have a video on that to help you get started. See the description for a link. We can have up to 4,094 VLANs on a switch. Of course, it would be rare to need that many. We only need 3 for now, which are for workstations, servers, and printers. When we're done, we can check out the VLANs that we've created with Show VLAN Brief. You can see the 3 VLANs that were created, and a few others. For example, Cisco reserved 4 VLANs for special use. We can't move or change these. It's interesting to know that historically, Cisco broke the VLAN range into 2 smaller ranges. VLANs 1 to 1001 were known as the normal range, while VLANs 1006 to 4094 were called the extended range. Keep in mind that this is just a Cisco thing. Other vendors don't do this. The other VLAN that we didn't create is VLAN 1, which is the default VLAN. Until we make any changes, all ports are members of this VLAN. We'll talk a bit more about this one later. So I hope this is all making sense so far. Here are 2 more questions to help you think about it and to challenge your understanding. What if you have a lot of switches? Let's say you manage the network for a university campus, which might have 500 switches. Wouldn't it be nice if we didn't have to configure VLANs on each one? Years ago, Cisco created a technology called VTP, or Virtual Trunking Protocol. This is no longer in the exam, but you might see it in the real world, so I'm going to give you a brief overview. VTP would allow us to configure VLANs on a single switch, and then have this configuration automatically pushed out to all the other switches. This means that we wouldn't need to go and configure each switch manually. So to make this work, switches are configured as one of 3 modes. They can be server, they can be client, or they can be transparent. Servers are configured with a list of VLANs. One or more server switches send this list in terms of VTP messages, which go out to all the switches in the VTP domain. The VTP domain name is also included in these messages. Client switches receive these messages and will pass them on to other clients. In addition, they automatically configure each VLAN they see in this list, as long as they are part of the same VTP domain, of course. The result is that you only configure the VLAN on the server switch, not on all switches. Be warned though, the VLAN list overwrites whatever is already configured, so if you make a mistake on the server, you may cause a problem across all switches in your network. Transparent switches, they'll see these VTP messages, but they'll only pass them on. They don't configure any VLANs themselves. In the case of these switches, they will still need manual VLAN configuration. Over time, a lot of people found that VTP was quite frankly more trouble than it's worth. As we said, a single mistake can bring down your entire network. Plus, there are better ways to configure your switches from one location, which we'll talk about in another section of this video series. So, my personal recommendation is that you set your switches to transparent mode. This will ignore any VTP messages that are seen, and your VLANs won't be overwritten. If you run the command show VTP status, you can see what mode your switch is in. In this case, you can see that the switch is a VTP server. So to change it, I'm going to jump into configuration mode, and I'm going to type in VTP mode transparent. There is a danger with putting a switch that has been previously configured into a live network. Can you think of what that danger might be and how we may avoid it? We need to add interfaces to VLANs, and when we do, we have two options. We can configure access ports or trunk ports. Access ports are the interfaces that regular devices connect to. That includes workstations, printers, phones, and other devices like that. Trunk ports are most commonly used when we're connecting one switch to another switch. However, there are other cases where we might connect servers to trunk ports too. Let's start by configuring an access port. Under the interface, we set the switch port mode to access. We then configure the VLAN ID that we want this port to belong to. So now when we connect a device, all traffic entering or exiting this interface is part of that VLAN. To check which interfaces belong to which VLANs, enter the command show VLAN brief. Here we can see that interface gigabit 0/1 belongs to VLAN 10, which is in the workstation's VLAN. We usually think of an access port as belonging to only one VLAN. However, there is an exception. This is when we have a phone and a workstation connected to the same port. Usually, the physical phone will connect to the switch, and the workstation will connect to a port on the back of the phone. In a case like this, we will configure a VLAN for voice traffic. In this example, we'll make it VLAN 40 and we'll give it the name voice. Then we'll enter interface gig01 and configure it with an additional voice VLAN using the switchport voice VLAN command. When we run show VLAN brief again, we can see that the voice VLAN has been created, but it isn't showing up on that interface. I picked an interface that was down, unfortunately, so it's not showing here. So, to check this one, we can run show interfaces gi0/1 switch port. Here we can confirm that the voice VLAN is also configured on this port. Okay, let's go back to trunk ports. As I said earlier, these are commonly used when connecting two switches together. They're also used a lot when connecting to servers, as most servers now have virtual switches inside them, and virtual servers are connected to those virtual switches. We'll look at virtual servers and virtual switches a bit later in another section. Trunk ports are capable of carrying more than one VLAN at a time. They do this by adding a VLAN ID to each frame. There are two possible ways of doing this. The old way uses a protocol called ISL. This is out of date, so we're not going to look at that any further. The right way to do it these days is with an encapsulation standard called 802.1q. This takes the Ethernet header in the frame and it adds in a small tag. This tag simply contains the VLAN ID. So if a switch needs to forward a frame from one switch to another, it will add this tag, and then the receiving switch will know which VLAN that frame belongs to. This process is often called tagging, and you can probably see why. In fact, while Cisco refers to it as a trunk port, many other vendors will call it a tagged port. It's really simple to configure a trunk port. Under the interface, we first need to select the type of encapsulation. This comes back to those two methods I spoke of earlier, ISL or 802.1q. You'll notice the third option, negotiate. We'll talk about that soon. As I said, .1q is the option we want to use now. Next, we simply set the switch port mode to trunk. We can get a bit of information with the show interface trunk command. Here we can see the encapsulation type, as well as the VLANs that are allowed on this trunk link. By default, all VLANs are allowed, as long as they have been defined on the switch. We can limit our trunk to certain VLANs if we want to. This is called VLAN pruning, because we're pruning off the VLANs that we don't want to allow. Personally, I always set an allowed list of VLANs as a matter of best practice, rather than leaving them all on. Now let's go back to that interface, and then we'll use the switchport trunk allowed command to provide this list of allowed VLANs. I would like to issue a strong warning here. When we use this command, we will overwrite the existing list of VLANs that are allowed on this trunk interface with the list that we provide. Many people, including myself, have made this mistake and caused the network to go down. If we look at this interface again, we can now see that we've got an updated list of VLANs that are allowed. On occasion, some traffic will arrive at a trunk port with no VLAN tag. As you can imagine, we call this untagged traffic. There are a few cases where we might see this. For example, if a workstation is connected to a trunk port rather than an access port. Or when a cheap and nasty switch that doesn't understand VLANs is connected to a good switch. There's even some traffic that switches send to each other that's untagged. So you might be thinking, the receiving switch needs the tag to know which VLAN the traffic belongs to. So what happens when there is no tag? That's a good question, and one that has confused many people. But it's not as tricky as it sounds. On the trunk port, there is a special VLAN called the native VLAN. By default, VLAN 1 is the native VLAN. When untagged traffic arrives at a trunk port, it is assumed to be part of this native VLAN. So, by default, any untagged traffic will be part of VLAN 1. We can change the native VLAN to another VLAN if we want to. We just configure the interface with the switchport trunk native VLAN command and we give it a new VLAN ID. Notice that we're getting a few syslog messages reporting a native VLAN mismatch. This is because CDP, that is Cisco Discovery Protocol, has detected that the switch on the other end of the link still has VLAN 1 as its native VLAN. It's important that native VLANs match at both ends of the link. You'll even notice that Spanning Tree has blocked the link. We'll talk about that in 2 more videos' time. If you need to verify the native VLAN on an interface, use the show interfaces switchport command. When we do this, we can see that the trunking native mode VLAN is set to 10. You can probably work out how to tell if an interface is a trunk by using the MAC table alone. Can you see how it's done? Cisco provides an automatic option for configuring trunk links called Dynamic Trunking Protocol, or DTP. This is a Cisco-only option which is turned on by default. Earlier we used the command switchport mode trunk. This manually configures a trunk link. As long as this is configured on both ends of the link will be a trunk. But rather than manual configuration, we can configure the link as dynamic. There are 2 types of dynamic configuration called auto and desirable. The results depend on what we configure at each end of this link. First, let's think about the desirable option. If this is configured, the switch actively tries to make this link a trunk link. This will succeed if the other end is also configured as desirable, or auto, or trunk. Let's see the configuration for this. We have 2 switches connected to each other. We first enter interface configuration mode. Then we configure switchport mode dynamic desirable. Although you can't see it here, the switch on the other side of the link is configured as dynamic auto. If we run show interfaces trunk, we can see that the mode is set to desirable. In the status column, we can see that this link has successfully become a trunk link. When the auto option is configured, we're telling the switch that we're happy if this interface becomes a trunk, but don't actively try to make it so. That means that if the other end tries to configure the trunk link, this interface will agree, and the interface will become a trunk port. So you see that the particular combination of settings will determine whether the link becomes a trunk or remains an access port. One recommendation I can share is to avoid configuring one side manually as a trunk and the other side manually as an access port. We can dig up a bit more information with show DTP interface. It's not particularly exciting, but it may prove useful if you're troubleshooting. DTP sends messages between the 2 switches to convert a link to a trunk. If we want, we can disable this entirely by configuring the interface with switchport trunk no negotiate. This is something you might consider doing if you're connecting a Cisco switch to another vendor's switch, or you're connecting a switch that you manage to a switch that somebody else manages. Personally, I don't like to use DTP in practice. I always manually configure my trunk ports. I find it has a lower chance of security problems, like configuring a trunk link where there isn't supposed to be one. It's really up to your preference though. There are 2 more quiz questions for you to think about. Perhaps think about question 9 in particular, which involves adding more VLANs to a trunk link without breaking the ones that are already there. There's another way that you can test your skills. Most of the videos in this series will have a lab accompanying them on networkdirection.net. I've built them using the Cisco CML Lab software, but you can use another product if you want. Your options include GNS3, EVAN-G, and Packet Tracer. In this particular lab, you have a customer who wants this network built. You need to configure the 4 switches to meet their requirements. Once that's done, you can try out some troubleshooting. These labs are usually reserved as a bonus for Patreon supporters, but this one's available for everyone so you can see if you like it. Please continue to the next video where we will look at interfaces. This includes connecting interfaces, MTU and frame size, and troubleshooting interface status. Hope to see you there.